All right, good afternoon, everyone. Welcome to our fourth session of day 2 for the 2020 virtual SHRUG webinar. Today I want to welcome Christy Crandall, who will be talking about a new method for identifying and prioritizing hydrologic restoration and increasing water yield. As always, we will be recording this session and we'll be distributing them either tonight or tomorrow. If you have any questions, please feel free to type them in the question box, and I will try to get to as many of them as I can before our time here today ends. So with that, thank you everybody, and I'm going to pass it over to Christy.
Okay. Good afternoon, everyone. Can you hear me? I'm taking that as a yes.
I can, yes.
Okay, good. All right. So, all right. I've been working on my. I'm a doctoral student at Florida A&M University in the School of Environment, and I also am doing my dissertation in the Center for Spatial and Ecological Restoration with the cool acronym of CSER. And so they're focused in the School of Environment, and they're working on using GIS and drone methods for restoring the Apalachicola region and others. But okay, with that, I'm going to get started here. All right. So, let's see. Let me see if I can minimize this. Well, the control panel. Get it out of my way here. There we go. That's a little smaller. Okay, so what my dissertation topic is I've been tasked with, I'm tasked with developing a new method to try to increase water yields or freshwater availability in the Apalachicola region, and we're going to be doing this with a particular area of hydrologic restoration in pine forested areas of the Apalachicola, and this method should be applicable to other forests in the northern Gulf region, other pine forests, that is. So these are my co-authors. And okay, so over the last 50 years, the Apalachicola region has experienced a loss of fresh water availability, and part of that is due to upstream water demand from irrigation and increased population in urban areas, as we are aware of. But it's also partly due to forest management practices. And this is an area where it's in Florida. It's areas where we have a lot of public land, and so we have more control over it than we do what goes on in the upstream basins. So due to the lack of fresh water, or the loss of fresh water quality and quantity, it's also caused a degradation and a loss of area of critical habitat that is for threatened and endangered species. And some of these populations have been reduced to critical levels, or even what is now thought to be extinct in a lot of the forested areas of the Apalachicola region. So my project, that's why we need more fresh water in the Apalachicola region. We want to restore and maintain the critical habitat for endangered and threatened species, and we want to go back to hopefully increasing the ecological diversity and improving the ecosystem function and sustainability in the region to what it once was, hopefully. This is just a picture of some of the threatened or endangered species. You see the striped newt, the frosted flatwood salamander, the gopher tortoise, purple bank climber, and some of the plant species that are also endangered. It's a red cockaded woodpecker over there. And these are the critical habitats that support these species. And The pine forest savannas and the upland pine palmetto forests are the areas that we're probably mostly going to be focusing on today. So the objective of my research then is to develop a scientifically based, flexible, scalable, and repeatable method to identify and prioritize pine forest areas for hydrologic restoration. And the major goal of this is to increase the freshwater availability in soils, which will increase the amount of water coming to streams and into the groundwater. And this method is also going to be generalized enough that it will be able to be used in other areas of the northern Gulf Coast forest. So the method involves, of course, first getting the data that we need to do this. And the most important data sets to this research are really good high resolution estimates of basal areas. And Joseph St. Peter did a presentation earlier today at SHRUG, but he's really amazing. He's come up with some great publications, and he's done some great work on teasing out basal areas from satellite imagery and other data based on ground truthing. And there's also another publication that he's been involved with that has been able to estimate the percent pine land cover by cell area. That's part of the most likely land cover publication. That is Hoagland et al. And Joseph St. Peter was also involved in that publication. So these are the two most important data sets that you need if you're going to try to use this method. Another data set that I used is the depth to the shallowest water. In some cases, it might be the surficial aquifer. In other cases, it could be the Floridan aquifer. But and then, of course, you need your, other things like your study area boundaries, but any meaningful boundary that delineates something that is critical, like a watershed boundary or a water divide, groundwater divide, or a forest tract boundary. These boundaries are going to be used to help us prioritize these areas for hydrologic restoration. So, of course, then we process these data sets, and these data sets are the pine and basal area data sets are raster data sets, as well as the shallow water table data set. And so we want these raster data sets to have identical cell areas, resolution. We also want them to be snapped so that they share the same, where the corners align. And of course, we project them to the same projection so that we don't have any problems when we go to clip them or compute areas or whatever. So those are just some of the regular stuff that we always have to do with geospatial data. So the first thing that I did with this method was quantify the amount of basal area that is attributable to pine. And so you can take your percent land cover of pine and multiply it by your basal area, and you end up with a basal area attributable to pine. And so that's the first step. Then from the current pine basal area, the whole point of this is to figure out where you are going to be reducing your pine basal areas so that you can increase the water yield to the soil and reduce evapotranspiration. So in this particular case, you can use your current pine basal area raster, and then you create some new basal area rasters based on what ecologically would be the best maximum basal area or the range of basal areas. So that's what you can do. You can set a maximum basal area, that any pine basal area in a cell that's greater than a certain maximum will then be set to your maximum value. So you'll end up, I use 3 different basal areas: the current basal area and 18 square meters per hectare, which is the maximum basal, like let's say density basal area that you would want to see in a pine forest for optimal ecological conditions. And then I used a lower level, which was 7 square meters per hectare as my maximum basal area, which is in the range. So the range of optimal ecological health for a pine forest is between 7 and 18 square meters per hectare. So I ended up with 3 pine basal area raster data sets. One that was set to current levels, one that was set to a maximum of 18, and then one was set to 7. Anything less than the maximums were just, they set to the current value of basal area. If you have any questions, let me know. So then from basal area, you can calculate leaf area index from the pine trees. And this is a global relationship between pine basal area, or between basal area and leaf area index, that was developed by Matt Cohen from University of Florida in a study he did that was published in 2018 for the Florida Department of Agriculture and Consumer Services. But so this is pretty much considered, there's global relationships for leaf area index and basal area in the literature. They vary slightly, but they're similar. But this is one that was developed for pine forests in Florida. So this is what I used for calculating leaf area index of my 3 basal area rasters for pine. This equation also was published with Cohen et al. 2018, and this is from leaf area index. This is where you bring in your depth to water, which is DTW raster, and this is a general linear model which describes a relationship between leaf area index, depth to water, and what's called the aridity index and water yield potential. So the aridity index is a ratio of the potential evapotranspiration to the mean annual precipitation. And there's some literature published about this, but in our area of the Apalachicola, 0.92 was a pretty good average value of the aridity index for pine forests. Depth to shallow groundwater, the raster was used that was created, that was snapped and aligned with the basal area and LAI raster. So anyway, so you get a new raster for each basal area raster of water yield potential. And you can see this one has a very good R² value. Once you have the water yield for each basal area, then you can compute the change in water yield based on the basal area reduction level. So that so I computed the difference between each of the water yield rasters that were created with each basal area raster. I see I have a typo on this one, apologize. And so now I end up with 3 levels of water yield gain between the current level of pine basal area and 18 square meters per hectare as the max, or the current basal area down to 7 square meters per hectare, or also between the 18 square meters and the 7 square meters per hectare basal areas. So I end up with 3 different water yield gain depending on how much you want to reduce the pine basal area in your forest. So using, so then you can look at these cell values. I mean, this is the grid cell size for these rasters is 10 by 10 meters over the entire Apalachicola region. So there's over 351 million cells of value in each raster. So you can look at the water yield gain rasters, and you can see, like, if you use the symbology and set the colors to bright red and grade into colors depending on low to high values, but you can't really, you know, synthesize it, and you can see where there's areas, but not real well. So I then use zonal statistics on the water yield gain rasters. And to make it relevant for water yield, one of my zonal boundaries was the HUC 12 watershed boundaries from USGS, because this is going to show, you know, I ran zonal statistics on the watersheds using for the water yield gains, and it gives you all the statistics, the count, the minimum, maximum, the mean, the sum, and the percentiles. And you can see which watersheds might gain the most if all of the pine basal area were reduced to either 18 or 7 square meters per hectare. So you also can use something else like forest compartments. I know the Apalachicola National Forest calculates tree information, tree metrics by their compartment numbers. So that's something else that could be useful for this particular, the land that's in the National Forest. But anyway, once you look at these maps, you can see which watersheds stand to gain the most water in water yield if basal areas are reduced to specified levels. Once you get your watersheds identified and your forest compartments, then you can focus in on the data within that watershed or forest compartment and do something like a hotspot cluster analysis, which really makes the forest stand information pop, that shows the highest capacity for water yield gain if it's thinned. So this was something, and the good thing about the hotspot analysis is it provides significance levels, so you can see the 99th percentile areas and the 95th and 90th percentile for very localized regions. I wouldn't recommend doing this in a large area though, because it's very slow. And you have to make points out of your raster data, which is clunky. So here's an example of my method in the Apalachicola Regional Study Area. This is the Apalachicola Regional Study Area that we were working with. And so first we had to get the relevant data, and like I said, the basal area was St. Peter et al. Was just published in 2019. That is published at the 1 meter resolution raster data. Hoagland et al. 2017 published a most likely land cover and included a pine percent cell cover. So that was those two are critical. The depth to the shallowest water table and groundwater was published in 2017. Arthur et al. By Florida Geological Survey, and also the Florida and Aquifer Potentiometric Surface, Chroma 2019. We had our own regional boundary, and then the USGS HUC 12 watershed boundaries, and the USDA Forest Service compartment boundaries, which is a timber metric. So all this data was processed like before, and this is showing you the current basal area published in St. Peter et al. 2019. The current basal area ranged from, now this is all the basal area, not just pine, but everything ranged from 0 to 97, basically, square meters per hectare. And you can see where Hurricane Michael came through. But it's still very dense over here especially on the east side of the river in the Apalachicola National Forest and Tates Hill State Forest. So this is the percent pine per cell, and the percent pine per cell ranged from 1 to 87% of the 10 by 10 meter resolution grids. And you can see we have some very high percent pines on the east side of the Apalachicola River in this region. These regions here, there's some over here also. And then when you multiply those two together, you end up with the current pine basal area. And this ranged from 0 to 57.5%. And you can see you still end up with some pretty high percentage pine basal areas on the eastern side of the Apalachicola River. If you use our formula here to compute leaf area index, of course it always has an intercept, so you never have 0. But the leaf area index for pine ranged from 0.3 to 4.5, and of course mirrors the basal area for pine. This is depth to water. Now this was kind of interesting because you always want to look at the topmost water aquifer, and the superficial aquifer is in the southern part of the study area here. But in the northern part of the study area, the Floridan aquifer is the top aquifer, and the potentiometric surface is closer to the surface than any other water. So you end up with, this is the Cody Scarp, basically, and you end up with the Floridan aquifer as the top. But it's still much, much deeper than the superficial aquifer, where you actually have a lot of areas. The blue areas are above, anything negative is above land surface. So of course these are rivers and lakes and stuff. The green, starting with the lightest shade of green is, so this is in centimeters. So the very light green is less than 1 meter from the surface. So you see a lot of the area in the eastern part of the east of the Apalachicola River is less than 1 meter below land surface, and the rest of it is less than 3 meters below land surface, pretty much. So all the areas where the superficial aquifer, you can clearly see. So if you use our equation to calculate water yield for the current pine basal area, you can see that you can clearly see the rivers, and where you have the positive water yields, those are areas where basically the water is closer to the surface. Where you have negative, that indicates that it's going to use more water than, it's got a negative potential, so anything that falls on the land is going to be sucked in it. So the water yield is negative potential in these green areas, very negative in some areas. So when you compute the difference in these water yields potentials, you can see, and this is just a small section just to focus in, and you can clearly see areas. Now this is showing you what the water yield gain might be if you reduce the basal area from current levels to 7 square meters per hectare. And the water yield gain is in centimeters per year. And so these are some of the areas on the western Apalachicola National Forest that have fairly high basal area. And so you're not changing anything else. Now the depth of water and aridity index is constant for the cell. Now but it's the basal area and leaf area index that changes here to give you a difference in water yield. And you can clearly see these areas that show. So this over the whole Apalachicola study region, the potential gain from reducing your basal area from current to 7 square meters per hectare range from 0 to 29.4. That was our max. This is just to show you what you end up with. So in order to help prioritize this by region and identify areas we would want to focus basal area reduction efforts on, I use zonal statistics, and the value that I was most interested in from the zonal statistics was the sum of this water yield gain, and this is showing you the watersheds. I then computed the 25 most the 25 greatest watersheds that would produce the most water yield gain if basal areas are reduced from current to 7 square meters per hectare. And this isn't all of them, but this is most of them. They mostly all occur here along the southern edge of, and on the east side of the Apalachicola River. This is using zonal statistics by forest compartment, and it shows you the forest compartments that, if basal areas are reduced, will give you the most gain in water yields. And of course, the red is the hottest, gives you the highest water yield gain. And then I've overlaid the top 25 watersheds, which doesn't actually show up that much, but you can see that within some of the, like the 25 top watersheds, you can pick out forest compartments to focus on. So you can use anything that's critical to your study and your objectives. You could use whatever works for your project. To go further, I used the hotspot analysis and cluster analysis, and this shows you the darkest reds are the 99th percentile of water yield gain. So these are getting down now to the forest stand level. So if you really want to focus your to maximize your water yield increases for amount of dollar you spend, you would want to focus in these areas that have the hot spots, the red spots. The black areas are insignificant, so as far as how much they can be reduced, but these areas right here would give you the highest. And you could make polygons out of these and compute, you know, an estimate of water yield gain. Those are reduced to levels 7 square meters per hectare from current levels. So in summary, this is a new method to identify and prioritize pine forest areas for hydrologic restoration with a goal of maximizing water yield increases. And we're going to be doing this by reducing pine basal areas. So this method was developed specifically for the Northern Gulf Coast regional forests, pine forests. And I demonstrated it in the Apalachicola region. And, you know, it requires basal area, an estimate of pine percent land cover by cell, depth to water, shallow water, and the aridity index. Everything's available out there, or it can be available. The method calculates potential water yield for different basal area scenarios, so you can calculate water yield gain by subtracting these from each other. So then we identify and prioritize them by using zonal statistics, and in my case, I used watershed boundaries and timber compartments. And then within these watersheds or forest compartments, I can further get down to the forest stand level using things like hotspot analysis within these watersheds. So this is a new method, a new way to use this data, and it is flexible and scalable and easily upgraded as we get new and higher resolution data, and hopefully improved relationships between basal area and leaf area index, or better relationships between water yield and the vegetation that's growing there. I mean, these things need more study for sure. Well, I'm quantifying water yield gain here based on how much basal area is reduced. I don't think it should be used as an absolute value of gain. I think that, that it's definitely best used as a qualitative indication, to identify and prioritize areas for basal area reduction. We need to do a lot more work on looking at errors that are associated with, because every single data set that I used has its own errors associated with it. And this is an area of research that, as a lot of you probably know, could be a whole dissertation on itself. But, like I said, there's 351 51 million values in these rasters, each one of these raster data sets. And if you try to do like a normal bootstrap on it, it just completely crashes your system in R, or so I tried that. But we can do things like, there's new stuff coming out all the time, and especially one that shows promise for big data analysis is a bag of little bootstraps. I don't know if any of you guys have heard that, but it's something definitely to look up. It's got a lot of promise for big data. While I was doing this, while I was developing this method, eventually I wrote Python script for it. It's pretty rough at the moment, but the eventual goal is to develop a decision support tool out of it. And so we have the bare bones of that right now, and we'll develop it further in the future. So I want to thank the Restore grant. My project was funded through an interagency agreement with the Gulf Coast Ecosystem Restoration Council and the USDA Forest Service, and Florida A&M University Center for Spatial Ecology and Restoration, and the Economies of the Gulf Coast States Act, the Restore Act. I want to thank them for funding this work, and hopefully we'll continue to build on this work to come out with some even better information in the future. And here are my references. So that's it. I guess, are there any questions?
That was great, Christy. Thank you for presenting. We got about 12 minutes left, so we'll give a couple minutes here for if there's anyone who'd like to ask Christy a question. Christy, from Janelle, do you have any contact information for those wanting to learn more?
Well, I do, but I didn't include it in my presentation. I can send it to you.
Okay, we are recording these sessions. So if you wanted to give out your email address, maybe,
Okay.
they could find it there too.
All right.
That's up to you though.
Yeah, that's fine. My email is Christy, that's CHRIS as in Sam, T as in Tom, Y dot Crandall, that's spelled CRAN as in Nancy, D as in dog, ALL at famu.edu.
Great, thank you.
Mm-hmm.
I have a question from Philip. Does connectivity play a role in choosing which HUC12s to modify? Are there benefits to choosing HUC12s that share boundaries?
Well, I didn't choose them per se. Those were the ones that came up with the highest sums. I mean, you could look at choosing your HUC 12s by, I know Northwest Florida Water Management District chose their areas for hydrologic restoration based on how close they were and connected to the Apalachicola Bay and estuary. So that, it depends on what your goal of your restoration is. Like in that way, they're also reducing their basal areas and doing other things. But in that particular instance, they are, looking at direct flow to the Apalachicola River Bay and estuary as one of their variables, like the timing and delivery and all that. Whereas in our case, that's not on this initial round. That could be in the next round, is doing something like hydrologic modeling to look at which basins would contribute the most, because as you get connectivity and flow through different basins, you may lose some flow through some basins, and some basins are closer to the Apalachicola River and things like that. So that's something we'll be looking at for the next part of my dissertation research. So we'll be making decisions about that.
Okay, great. It looks like that is all the questions we have for now.
Okay.
So I wanted to thank all of our attendees for coming out today. And again, I wanted to thank Christy Crandall for presenting. With that, I'm gonna close the session down. We do have one more session remaining for the day. And that one starts at 3 o'clock. So hopefully we will see you all there. Thank you everybody for your time. Have a great rest of your day.